Hello Python pals! Today we're going to be working with servo motors. These are motors that can rotate on a 180-degree arc, so let's get motoring. Now when coding servos in CircuitPython, all you need to do is specify the angle and the servo will rotate to that spot. Super easy. But before we code, I want to talk just a bit about motors. Now there are lots of different kinds of motors. Right now I'm working with a micro servo motor. It's a very inexpensive motor. This one happens to be a Tower SG92R that I got from Adafruit. Micro just means it's small. If you have a larger standard servo motor or even a sub-micro servo motor, those both should also use the same code that we learn in this lesson. Now you will notice that this motor has 3 wires. Those wires are for power, ground, and signal. That's just like our LED strips and strands. Most servos also come with a packet of plastic add-ons called horns. Now the horns are these plastic components. Servos come with a few different kinds of horns, and you can use a horn to attach a string to pull an object. Buddy's arm is on a string in this video here. You can also attach a popsicle stick or something that might be used to push open a lid. That's how the box is opening up to let somebody reach in to grab a candy cane. Now, a little bit about different kinds of motors that you might encounter. It's really important to pay attention to the kind of motor that you've got. You might also see a type of servo motor called a continuous rotation servo. Now that is not what we're working through in this lesson. It's actually a different type of motor entirely. Those servos allow full and continuous rotation, not just within a 180-degree arc, and setting those up and programming them is different. Now there are also DC motors which also offer continuous rotation. They're usually faster than continuous rotation servos, and we'll be using DC motors to power the wheels in a future robotics project. You'll find DC motors everywhere. They're in fans, they're in drills, and other types of electronics where you see something spinning. DC motors usually have just 2 wires. Power the motor and it spins, remove the power and it stops. You can also vary the speed as well, but that's for a future lesson. And another common motor type that you might encounter are stepper motors. Now steppers offer greater precision, and those would be a good choice in projects where you needed to have finer movements. Think a precisely moving robotic arm. You'll also find stepper motors used as controlling mechanisms for 3D printers. Now stepper motors require more complex wiring and control. They usually come with 4 or even more wires each, and you'd need to add an additional control mechanism like an add-on board to work with stepper motors. And I think that's enough for the types of motors right now. If you want to learn more about motors, there are lots of great guides online, including a motor selection guide at Adafruit that goes into how these motors actually work. If you looked inside of them, the guide discusses geared motors, brushed versus brushless motors, but that's much more info than we need to get these stepper motors working. Now, one more thing. For the kind of inexpensive servos that you're likely to use early on in your Python programming career, out of the box or bag, they probably don't move in the full 180-degree arc as advertised. But I'll show you how we can adjust that arc in our code after we set up the servo and make sure that it works. So let's take a look at the standard servo motor and connect it to our circuit playground. Now the wire colors might be different depending on the brand of servo that you're using, but they're usually red for power, brown for ground, orange for signal. If you have different colors, just search online to see if you can find a specification sheet or documentation for that servo. Now again, we see the 3 wires and we have sockets at the end of these wires. Now we could cut off the sockets, and in another video I show how you could do this with a light strand, and you can bolt the ground, power, and signal wires to the pads on your Circuit Playground Bluefruit. But instead of cutting these wires, what I'm going to do is I'll just use these additional wires that have pins on one end and alligator clips on the other, and I'll insert the pin end into the sockets on the servo and clip the alligator clips into my Circuit Playground. By the way, if you're ever using jumper wires, the colors on the wires don't mean anything. The internals of the wires are all the same. They're colored just to make it easier to distinguish one wire from another. But these wires that I'm using are actually terrible because the wrapping material on the alligator clip is different from the color of the wire itself. So I need to make sure that I'm actually plugging the correct wire into the correct pad. Also, make sure that you've unplugged your CPB before you wire anything to it. It's likely going to be okay here, but powering devices down before changing the wiring is a very good habit to get into. Now to wire this up, I want to plug power into V out. Ground is going to any of the GND pins, and we can use any of the pads that we send a signal to for a signal wire, but in this tutorial, I'm going to use pad A2. So with your servo motor wired up, you can plug your CPB back into your USB port, and let's get this thing cooking. So in working with a servo, you need just 2 libraries. PWM-IO, because servos are powered by pulse width modulation, or PWM. That library is built into CircuitPython. And Adafruit_motor, which you need to install in your LIB folder. We'll use circup for that. And if we're only working with servos, we can get away with importing only the servo module of the Adafruit motor library. Now, even though servo motors use PWM, the specifics of how PWM works is not important to you as a programmer. It's really hidden from you, but if you're curious, PWM stands for pulse width modulation. The width of the electrical pulse will determine the angle of the servo arm. Wonderfully, CircuitPython hides these details from us, and as you'll see, you just need to set the angle and the servo arm will move to whatever number you pass in. Now, you'll also want to import board and time. We've already been doing that, so add in these two extra libraries and you're good to go. Then we're going to create a PWM out object, and we're going to use that object to create a servo object. So in this line here, I'm going to call the PWM out object PWM. That's a good name for a PWM out object. And I'm going to use the PWM-IO library's PWM out class to create that object, and I'm going to pass in the location where I attach the motor's signal wire. So in our example, this is going to be board.A2. If you attach your motor to a different pin, make sure that you use the different pin number. Servos use 50 pulses per second or 50 hertz, so 50 is the frequency we're going to use. Now, once we've created this PWM object, we feed that into the servo class of the servo library and give the object you've created a name. Here I'm calling it servo_1. That's a good name because many projects have more than one servo, and that's it for setup. Then to use the servo, we just use its dot angle property. We set that equal to a number between 0 and 180, and that will swing the arm to that angle. That's all it takes, so let's give this a try. So with your servo plugged into your board, plug your board into your computer, and if you're new here, welcome. You may want to check out the earlier lessons in the playlist so you know how we got here. So since this is the first time we're using the Adafruit motor library, we should import that package into PyCharm so we get code completion and error handling, and we'll use circup to install that library on our board's lib folder. So let's head to PyCharm's setting menu, and under your project, select Python interpreter, then click the plus sign. Then the library we want is Adafruit motor, so I'll search on the word motor. There are a lot of options that show up here, but remember, all of the CircuitPython modules start with Adafruit-CircuitPython, so this is the module we want with -motor at the end. With this selected, click Install Package, then Close, then OK. Then we can open the terminal, and at the % prompt, we can type circup install Adafruit_motor, press return, and all the modules we're going to need are installed on our board in its lib folder, and we're ready to code. So let's enter a comment up top that says servos.py, and we'll import board, time, PWM-IO, and also from Adafruit_motor, we're going to import servo. Then let's set up the servo. So first I'm going to create a PWM out object with PWM equals PWM-IO dot PWM out, and that's with capital PWM and O, and I'm going to pass in the pin number that the signal wire for the servo motor is connected to. In our case, that's board.A2, and the only other parameter that we need is frequency, and I'm going to set that equal to 50. And now that I've created the PWM out object, we're going to use that to create a servo, so I'm going to name my servo servo_1. We're going to set that equal to lowercase servo dot uppercase servo. We'll pass in the PWM object we just created, and our servo is set up. Now, as I mentioned in the intro, you almost always have to calibrate the servo you're using, and calibration just means that you'll make some changes in your code to get the servo to swing properly. You're actually changing your code, not the servo itself. And then once the servo's calibrated, you'll be able to write code and expect reliable movement. And we'll return to this slide and I'll explain it in just a bit. Now here's an example of my servo being off. I've written code to sweep from 0, pointing out to the right, to 180 degrees, pointing out to the left. But this servo's angle is smaller than the 180 degree angle. See how the farthest left point doesn't quite form a straight line with the otherwise straight 0 value when it points to the right? Now we can fix this by tweaking our code, but first I want to test my code to make sure that it's working, and then I want to end up at the 0 degree mark, and then I'll add the horn at a straight line, assuming this will be my base 0 point. So for me to test my code, I'm going to move to the 180 degree mark, then the 90 degree mark, then the 0 degree mark. If things work, I'm going to insert the horn, and then I'll show you how to calibrate the servo for a more accurate 0 to 180 degree swing. So back in our code, we're going to first work without a while true loop. Let's start by saying servo_1.angle equals 180, and then in time.sleep, I'll pass in 1.0 to add a 1 second delay. Adding the delay is very important. Then I'll copy these two lines, paste them down below. The second time I set the angle, I'll set that to 90 degrees, and the third time I'll set it to 0. Then let's save, open the serial console. I've got no errors. I can hear the servo moving. So now I'll slide the arm-style horn onto the servo, and there are little teeth around the horn and the connection on the servo itself so that you can position the horn anywhere you want in a circle, but I'm going to choose to point the arm off to the right, and let's run the code again to see how far off our servo swing is. So yep, just as we showed it, we're not swinging to 180 degrees. Hopefully when we fix that, we'll also point straight up for 90 degrees. And just to show you how it goes from 0 to 180, I'll reorder these lines of code from 0, 90 to 180. We'll run one more time. 0, 90 leans to the right too much, and 180 leans even more to the right. So here's how we can fix this by adding and adjusting two optional arguments that we pass in when we create our servo object in our code. Now when we created our servo, we initially didn't pass in these two arguments that you see here, min_pulse and max_pulse. When we don't pass them in, the default values are 750 for min, 2250 for max. But if we increase the max pulse more than 2250, we swing the arm out further counterclockwise. Pass in a max pulse less than 2250, and we'll swing the arm inward or clockwise, reducing the angle of swing. And if our 0 degree angle needs tweaking, well, we could pass in a min_pulse value less than 750 to push the angle outward or clockwise, or we could pass in a value more than 750 to push the angle counterclockwise or inward. Now there is a limit to these values. Try values less than 500 or greater than 2500 and you probably won't see any results. Also, if you change a value and you start to hear your servo vibrate when it's supposed to be idle and not moving, then you're pushing your servo too far, and you'll want to ratchet back your settings so that they're closer to the defaults. Again, when working with these inexpensive servos, remember these motors are cheaper than a latte at Starbucks. Sometimes you won't even get a full 180 degree swing, but I'm going to try to calibrate my servo. You should try this with yours. You'll probably come up with different results. Let's head back to our code and give this a try. By the way, many servos also have a screw on them where you can adjust the angle. Sometimes you have to open up the servo to get at them. It varies by model. Most times it can be easier just to make the adjustments in code. Now, since I like where my 0 value is at, I'm not going to pass in a min pulse value, but since I want my 180 degree mark to swing further out counterclockwise, in this line up here where I create my servo, I'm going to pass in a max_pulse value. 2500 is the maximum max value you should pass in. I'll try that. I'll save my code. And it looks pretty good. And it looks like we're swinging fairly closely from 0 to 90 to 180 degrees. I think this is fine. You're welcome to do any additional tweaks on your own servo to get things working the way you'd like. And now that we've got our servo calibrated, how about a challenge? Now for this challenge, you have to go back and add code to work with the two buttons for your circuit playground. Remember button A and button B, and what we have to import and how we set those buttons up. If you need a refresher, you can check your code from an earlier lesson. And when you're done with this challenge, when you press button A and B simultaneously, you should see the servo arm rotate 180 degrees. Press just button A and you'll see the rotation to 0 degrees. Press just button B and you'll see the rotation to 90 degrees. Now remember, if your servo is already at that angle when you press the button, then you won't see any additional movement. And you'll also want to pause a short time, maybe 0.2 of a second after each button press and move. That'll just ensure that the proper motion and button press is detected. So give this a try. Pause. You can do it. I know you can. And resume, and let's compare answers. Now I'll delete my test code, and I'm going to add a while true loop. I want that, but also remember we've got to set up our buttons, so I do that by importing digital IO up top, and then I'll create my buttons. I'll say button_A equals digital IO dot digital in out, passing in board.button_A. Make sure you get your capitalization right or things won't work. Code completion will help you with the capitalization. And then let's make sure that the button is seen as an input device. So we say button_A dot switch_to_input, passing in pull equals digital IO dot pull dot down. Again, watch the capitalization. Code completion will be your buddy in helping there. And then I'll copy these two lines. I'll paste them below. I'll switch the 3 references to button A to button B in these 2 lines. Now I've got my 2 buttons configured. Make sure that you change that button A to button B in 3 places. And then go down to your while true. Always make sure you got a colon at the end of the while true. And we'll say if button_A dot value and button_B dot value colon. That checks that both buttons are pressed. And if so, just to make sure things are working, I'm going to print a statement out. In this case, I'll print 180 degrees in quotes. Don't worry if you didn't get the degree symbol, but if you care about those kinds of things, on the Mac to get the degree symbol, you type Shift Option 8. That's not at all necessary. And then the real magic, servo_1.angle equals 180. Then we want to outdent for our if statement, and this needs to be even with the indentation of the if statement, and we'll say elif button_A dot value colon. This checks if just button A was pressed, and we'll print out 0 degrees here, and we'll set servo_1.angle to 0. and then we'll outdent for one last elif statement. Remember, we need an elif here and not an else. It's very important. We're checking for a condition of truth here, so we need an elif, not an absence of truth in all the previous if or elif statements, which is what else would do. So this is elif button underscore b dot value colon, and then print 90 degrees, and servo underscore 1 dot angle equals 90. Then remember, we need to add a time sleep. This is important because we want to make sure if we have two fingers on the button, if we release one finger a tiny bit before the other, that we don't errantly record that as a button press, and it'll also give us enough time so that the servo can move to its new angle. So we'll outdent and say time.sleep, passing in 0.2. That should do it. And then we can save, open the terminal with TO. I see no errors. Great. And now let's give this a try. 2 button press. We rotate to 180 degrees. Nice. Button A press. Back to 0 degrees. Button B press. Straight up at 90 degrees. And you can keep pressing buttons if you want to try this out, but excellent work. And if you found this a challenge, you struggled to remember how to set up your buttons, or if you forgot things like colons at the end of while true, or if and elif statements, just keep practicing. You might repeat this exercise or an earlier lesson. Sometimes all you need is a little bit more practice to hone those coding superpowers. And before we continue, why don't we save this as 3-press-servo-moves.py to our CircuitPython school folder and close that outermost tab. And as further testing in our dojo of code awesomeness, let's try yet another challenge. So you likely noticed that our servo moved rapidly to whatever angle we set, but what if you wanted a slower sweep? Sometimes you want that, and you can code this. You have the skills, coder. So in this challenge, I want you to begin at 0 degrees and slowly sweep to 180 degrees. And the way I want you to perform this sweep is by traveling at 5-degree increments from 0 to 180, pausing 5/100ths of a second after each 5-degree move. Then, when you've reached 180 degrees, pause for half a second, start back in the other direction, moving 5 degrees at a time again, but this time moving towards 0. Again, pausing 5/100ths of a second after each 5-degree move, and pausing another half second when you reach 0. Continue forever, and when you're done, save this as servo-slow-sweep.py. You can do it, skilled one. Pause. Give this a shot. And if you need to, give it a double shot. And resume, and let us compare answers. So back in our code, let's change our comment up top to servo-slow-sleep.py. Then let's head down and delete what's under the while true loop. And I'm going to add 2 for loops, one for going from 0 to 180 degrees, and another going from 180 back down to 0. So for the first, I'll say for angle, and angle is just our variable name. Remember, we could use any name for this, I, X, index, but angle's a good name since we're going to be looping through an angle value, and we'll follow this with in range, and in parentheses, 0, 181, 5, and make sure you got a colon at the end. Why 181? Well, this will make sure that the range goes up to 181, but remember, we never reach that value. That means we stop at 180, which is what we want to do. Then below this, we'll indent inside the loop, and we'll set our angle, servo_1.angle equals angle, and then we'll pause for a bit with time.sleep, passing in 0.05. Now that we've reached 180, we want to pause for half a second, so outdent, time.sleep, passing in 0.5, and then I'll set up the for loop to go in reverse from 180 down to 0, and that's with for angle, and it's okay to reuse the variable name angle here because we're done with the loop that's above this, and we'll set this to in range 180, -1, -5, close parens, colon. Why the -1? Because we want to go down to -1. We never reach -1, so that means we're going to stop at 0. And why -5? Well, that's because we're starting at a high value, 180, and we want to go down by increments of 5. Subtracting 5 are -5. That's our increment value or our step value. And then underneath this, indented, we're going to say servo_1.angle equals angle. We'll sleep for 5/100ths of a second, then I'll outdent. I'm going to add another time sleep for half a second here. Then you can save and head to terminal. And oh, will you look at that magnificent, an elegant sweep, left to right, back and forth. Powerful Python peeps, you are well on your way to robotic coolness, and you can absolutely begin creating kinetic projects with all sorts of motion that can run on its own if it's triggered by a button press, a touch, or other sensed event. Keep building those skills, coder. Make sure you save this to your CircuitPython school folder as servo-slow-sleep.py and close that outermost tab. If you like these tutorials, please let me know. Share with others. Tell your educator buddies. And if you're an educator using this with your own students, let me know. If I've got a few extra stickers, I'll send them your way. And for all of our learners, whether you're students in my classroom or those out on YouTube, keep coding. More goodness awaits.